For this second part of section 3.3, we're going to talk about the ideas of concave up and concave down. To begin with, I have these two graphs that I wanted you to look at last time. And I want you all to ask yourself, what is similar and different between both of these graphs? Well, the first thing you'll see is that both of the graphs are increasing. Both the graphs are always going up. So this is an increasing graph, and this is an increasing graph, but they're not increasing in the same way. Notice this graph increases, but as it increases, the slope gets steeper and steeper. Steeper as we go that way, versus this one gets less steep as we go that way. One of the ways we'd like to say this in math is this increases, but it increases at an increasing rate. Whereas this increases at a decreasing rate. So if you think about this, that means this graph, it gets steeper and steeper and steeper. This graph gets less and less and less steep. So one way we might think about these is to think of them in terms of derivatives. And that is this first problem, if I were to try to draw the derivatives of it, the derivatives would always be positive, but they would start out at a small positive number and end up at a big positive number. So f prime of x starts small and gets big, versus over here, f prime of x is going to start really big and then get very small. So something like that. What we notice is that for this graph, f prime of x starts small and gets big. F prime of x is growing, is increasing, and here f prime of x is decreasing. So let me erase those and come back and write down this observation. And that is that f prime of x is increasing. And in this one, f prime of x is decreasing. Well, if the derivative is increasing, that means the derivative of the derivative must be positive, or what we call the second derivative is greater than 0, versus over here, our second derivative is less than 0. Well, this is exactly what we mean when we use the words concave up and concave down. So this one is what we call concave up, and this one is what we call concave down. So let me just summarize these two pictures and summarize what we mean by concave up and concave down. Concave up, there are two things we should know. First thing we should know is that the derivative, or the second derivative, is greater than 0. The second derivative is positive. Versus concave down, the second derivative is less than 0. It is negative. If we want to think of this in terms of pictures, concave up is a picture where you have kind of a bowl type shape. Or you could have a bowl type shape that looks like this, or you could have a bowl type shape that looks like this. You could have just half of the bowl. But at any rate, it has kind of an upward facing bowl, versus concave down is what we get when we have a downward facing bowl. So a shape that looks like this, or it doesn't have to ever actually curve, but it can have that same bowl shape and just continue growing always. Or similarly, it could just be one half. So you can have half of the bowl at a time, but it's always kind of got that bold shape. That we call that a concave down shape. Okay, so this is what it means to be concave down, and what we want to do right now is we're going to tackle the question of how do we determine if something is concave up and concave down. And to do that, let's revisit the last video. And in the last video, we had a method for deciding when an equation was increasing and decreasing. It was increasing and decreasing. We found all critical points of our function. Well, what were the critical points? Those were the points where the derivative was equal to 0, or the derivative did not exist. So we found all critical points. We found all points where the derivative was 0 or didn't exist. We placed those points on our number line, and then we tested each section. How did we test each section? We used the first derivative to test each section. So we put that point in the derivative to see if it was positive, then we got a concave up point, or a increasing point. If it was negative, then we got a decreasing point. So this was the increasing and decreasing method. Well, now what we're going to have is we're going to have the concave up, concave down method, which really is the exact same method, except instead of using first derivatives, we're going to use the second derivative. So concave up, concave down, instead of saying when the first derivative was positive, now we're going to look at when or was 0. We're going to look at when the second derivative is 0, or when the second derivative doesn't exist. We'll place those numbers on a number line, and now instead of testing them with the first derivative, we'll test them with the second derivative. So the concave up, concave down method and the increasing, decreasing method are actually the exact same method. We do them all the exact same way, except this one uses the first derivative, and this one uses the second derivative. Okay. So now that we're on this, let's come and tackle this 3.8 problem and see if we can make sense of this problem using concave up and concave down, using this concave up, concave down method. Okay. So we're on exercise 3.8, which we're revisiting an equation that we saw earlier. This was exercise 3.6 equation. So we're revisiting 3.6. And we had our function. Our function was f of x equals x to the fourth plus 8x cubed plus 18x squared. And then last time we used the first derivative, which was 4x cubed plus 24x squared plus 36x. And then this time we're going to now take another derivative and figure out what's going on when we take a second derivative of this problem. When we take a second derivative of this problem, we end up with 12x squared plus 48x plus 36. And so here's our problem. And now what we want to do is we want to figure out every point where this either equals 0 or does not exist. And of course it always exists, so equals to 0 is really the only option. So we're going to have f double prime of x equal to 0, and we're going to solve that equation and hope that we can be successful. So let's start solving that. 12x squared plus 48x plus 36 equals 0. I'm going to start by factoring out a 12, and I'll have x squared plus 4x plus 3 equals 0. And then we'll come up and we'll do one more step, and the next, and okay, so now I'm going to see if I can factor it, and it looks like I can factor it. A little bit surprised that I can, but it looks like we've got x plus 1 times x plus 3 equals 0, so it looks like I've got x equals negative 1 and x equals 3 for my solutions. Hold on just a second. I want to make sure that I'm making sense of this problem. I mean, I know how to do the problem. I just want to make sure I haven't messed up my algebra yet. Okay, good. That looks good. Okay, so we've got x equals negative 1 and x equals negative 3. So what am I going to do with these 2 points? I'm going to put them on a number line, and I'm going to put negative 1 on my number line and 3 on my number line. And then once I put those 2 on my number line, then I can check each section to see if each section is concave up and concave down. Okay, so I just check each one, and that means I pick some point to the left of -1. And what's a point to the left of -1? -2 is a good point. So that means I take -2 and I put it in this second derivative equation. This is a good one to put it in. So let's do -2. Here, let's get ourselves plenty of space over here. Sorry, I'm fumbling around. You all are patient, and I appreciate your patience. Okay, and so this one, so I'm going to do 12 times -2, -2 plus 1 times -2 plus 3. And we'll put all this together. So this is 12 times -1 times +1. And so it looks like -12 is what we get. So this is a negative number. And so what does that mean about the graph? That means the graph is concave down on that section. Okay? Now I picked a number between 1 and 3. And by the way, probably 0 is the best number to use here. You can also use +1, but 0 sure seems like the right choice, doesn't it? So I'll put 0 on here, and this will give me 12 times 0 plus 1 times 0 plus 3, which is 12 times 1 times 3, which is 36. And so that means it's positive between that section, so it means it's concave up on that section. And finally, I'll pick a number bigger than 3. How about 4? I mean, I guess I could pick something really, really big, but 4 seems pretty sufficient. And that'll be 12 times 4 plus 1 times 4 plus 3. Uh-oh. Oh, I messed up. Again, I messed up. Look at this, people. This is why I was worried earlier. Man. Okay. I think I messed up. Okay, there we go. So this is actually a -3 and a -1. So let's fix all of these. And sorry, so when I factor x plus 1, x plus 3, that gives me a -1 and a -3. Why did I do... I'm frustrating myself. Sorry about that. Well, 2 of the numbers I've already done. I did -2. X equals -2, and that was a negative number, which made this concave down. And then over here, I did 0. X equals 0. And that was positive, which gave me concave up on that section. So now the only section left to think about is this section over here, which is less than -3. And we'll use x equals -4 instead of +4. And so we'll get 12 times -4 plus 1 times -4 plus 3. And that's going to give me 12 times -3 times -1. But it looks like a positive 36, so it looks like this is positive, which makes it concave up. And so what we can see from our graph is that our graph is going concave up, concave down, and concave up. Okay, so now what I'm ready to do is I'm ready to go back to that problem that we had earlier and see if I can get a better picture of what's happening on it. So let's see if I can find my graph from earlier. Let's see, I can't, I think I erased it. That's too bad. Okay, so, but from last time, what we had was we had a graph that looked like this, that had -3 on it and 0 on it, if I'm correct. So I think it had 0 and -3. Hold on, I'm just checking to make sure I'm doing things right. All right, 0, -3, and our function was decreasing, and increasing. So I believe that's what we had from last time. So what did that mean for our graph? It meant that we were going down, and going up. So we had some picture of what our graph was doing. But now what we can do is we can take that exact same picture and make it look even better. Because what we know is that from -3 to -1, tell you what, let's move the 0 over here. From -3 to -1, our graph is concave up, concave down, and concave up. So that means we can take our graph and put all of this information on it and start to get what a graph that looks really, really good. So we'll put -3 over here, 0 over here, -1 over here. And so what our graph is doing is in this section, so in this section, which is this section of our graph on this side of -3, what is it doing? It's decreasing, but it's decreasing in concave up. So what does a decreased concave up look like? It's going down, but it has an upward bowl shape. So on this section, it has that type of shape to it. So that's what's going on in that section, and then we can see that it's going to have an arrow pointing here. And now then, what we get is that between -3 and -1, it's still decreasing, but now it's decreasing with a concave down shape. So in this section, it's now having that type of shape to it. So we see that it's still decreasing, but the way it curves changed between -3 and -1. Now finally, between -3 and 0, what happens is it continues decreasing, but it switches back to concave up. So it switches back to this concave up shape, and then what happens at 0? At 0, it now increases and concave up. So what we see is that it's concave up, concave down, and concave up, and then when you add the decreasing, decreasing, and increasing, you can start to get a pretty good picture of the graph. And this is really what that graph looks like, except I think the y-axis is lower. So if you were to go grab your calculator and just type in the graph and look at it, you would see that it has this basic shape overall when you look at it. The one other thing you might want to do is just like put 0 or something in the equation, and I think you get 0. So I think the y-axis is actually right here, so it's a little bit lower. Okay, there's a lot going on here, so I hope that that this didn't overwhelm you. But that being said, let's talk about one important point, actually two really important points, and that is this point right here and this point right here. And these are points that we call inflection points. So what is an inflection point? An inflection point is a point where we switch from concave up to concave down. So just like minimums and maximums were points where we switched from increasing to decreasing, inflection points are points where we switch from concave up to concave down or concave down to concave up. So what is an inflection point going to look like? An inflection point has some sort of property that looks like this. Either it's concave up to concave down, and so it has this type of shape. And what you see is that an inflection point is where it kind of the curvature starts changing or makes a big adjustment. Or it could be one to where it's concave down and then it switches to concave up. So we could have some sort of shape that looks like this. It's an inflection point. Inflection point is a point that you hear a lot in culture, and people say the inflection point is the point like where all the patterns changed, the trend switched to a new trend, and you can see that for this inflection point we're trending in one way, and then when you hit that inflection point it switches and you start trending the other direction. So inflection points end up being points that have either. So let me give you a couple examples of the same type of inflection point. So we'll do concave up to concave down, or we could have concave up and then here we can switch to concave down. And so here's our inflection point where we switch, and here's our inflection point where we switch. And what you can see is that the inflection point is that point where the trend changes. So it's either, in this case, notice they're all really steep negative slopes, and this is the least negative of the slopes. And here it becomes positive, and the inflection point here is the steepest positive slope as we move across. By the way, there's an important inflection point that shows up right now as we talk about the coronavirus. So if you start thinking of, if you were to plot a graph of cases, total cases of the coronavirus, what is going to happen in the long term is that our total cases for the coronavirus are going to grow, and they're going to start growing really steeply. And we are right now, as the time that I'm taping it, we're somewhere around here, right? Where if you look at our graph, this is all you see, that it started out really small and it's starting to grow steeper and steeper. It kind of has an exponential growth to it. But what's going to happen is that at some point, everyone who is, the number of people who get sick is going to start to decrease, either because we've done a good job social distancing or because we've made some medical breakthroughs that have allowed us to prevent cases, or everybody gets sick. So if everybody has gotten sick, then the number of people that get sick starts reducing. So what's going to happen is our total number of cases is going to level off, and we're going to have some level off point. And really, probably the most important point in the whole game is this inflection point. And so what we're looking for right now, when we're kind of looking at coronavirus stats, and by the way, I'm such a nerd, every night I Google coronavirus stats and just look at graphs of the coronavirus. My wife, I think, laughs at me a little bit. But what we're looking for, what I'm looking for, what everyone's looking for is this inflection point. Because once we see this inflection point, then that's a sign that things are starting to change, and that this flattening out period is starting to reach, and that we're about to reach our maximum number. So at any rate, this is a phrase that's being used today in our language. Okay, let's move to the next problem. I'm going to skip, so 3.9 we're going to do later. So 3.9 will be later. I'll make my own video for section 3.9. So we're going to try that one out and do it at a later section. But right now, we're going to flip over and we're going to do exercise 310. We're going to do exercise 310. And this would be a really good time for you to pause your computer, push that pause button, try to do exercise 310 with the cosines, see if you can figure out where that thing is concave up and where it is concave down, and then see if you can blend that with the answer that you got last time. All right. All right, so we had x plus 2 cosine x, and last time we took the first derivative, which gave us 1 minus 2 sine of x, and I believe, if I remember correct, that when we had our graph, we put 0 and 2 pi, and if I'm correct, we had pi over 6 as being one of our important points, and 5 pi over 6 as being the other important point. And I think that this graph went increase, decrease, and increase. So I think that was the shape of the graph. It went up, down, and then up again. So I think that was what happened here. Let's see, is that right? Yeah, I think that's right. Maybe I should check, but I will in a little bit. Okay, so so what are we going to do now? So now we're going to talk about the second derivative. So let's grab a blank sheet of paper and try that, or whiteboard, if you are like me. And so let's look at the second derivative of this thing. And the second derivative is not so bad. The second derivative is, the derivative 1 is 0. The derivative sine is cosine, so it's negative 2 cosine of x. So we just have to figure out where is cosine of x positive and where's cosine of x, or where's cosine of x equal to 0 and where does it not exist. So notice this always exists. How do I know it always exists? It always exists because we never have a spot where we're dividing by 0 or taking the square root of a negative number, or it's not a tangent or secant that have an asymptote in it. So this always exists. So now all we have to do is I just have to solve this problem equal to 0. So I'll do negative 2 cosine of x equals to 0. And this is just the same as figuring out where cosine of x equals 0. And if you go back and think about your unit circle, cosine is the x values of the unit circle. So cosine is 0 here and here. And so we have two values where it's equal to 0. It's equal to 0, pi over 2, and 3 pi over 2. So we just have those two values. We have pi over 2 and 3 pi over 2. And so now I just have to make my number line and test my number line. so as I make and test my number line, what I get is, I'll write my second derivative on here again, negative 2 cosine of x. And we've got 0 over here and 2 pi over here, and then we'll put pi over 2 in that section and 3 pi over 2 in that section. And now I just have to test each section. So let's test something between 0 and pi over 2. Pi over 4 seems like a good number to test. So let's put negative 2 cosine of pi over 4. You may know pi over 4. If not, you can check it on your calculator. But it's the square root of 2 over 2. And so this ends up being negative square root of 2 for your answer. So this is negative, which means that our graph is concave down between 0 and pi over 2. Okay. Let's try something in between here. Pi seems like a good number to check in here. And so let's do negative cosine of pi. Negative 2 cosine of pi. Cosine of pi is negative 1. So this ends up being positive 1. And so we get a positive number here, and we're concave up on that section. So we're concave down, concave up, and then our very last section we'll do, how about 7 pi over 4. And this is also going to give us a negative square root of 2 when we're done. So this is negative, and this is concave down. Oh, what is this? So this is just the number that's pi over 4 away from making a full circle. So if I did my unit circle, I chose that number, and then that number. Because cosine is the x value, those two end up gave me the same result. Okay, so I got concave down, concave up, concave down. Okay, so now I'm ready to take the results that I had earlier with this increasing, decreasing, increasing, and this results where I had concave up, concave down, concave up, concave down, and I'm ready to try to put all of these together onto the same graph in order to get myself a really good graph of the cosine function. And so let's try to do that and see if we can make sense of it. Okay, so what I'm going to do is I'm going to put my number line here along the bottom, and let's put 0 here and 2 pi right here. And the numbers that I need is pi over 2 and 3 pi over 2, and then pi over 6, and then 5 pi over 6. And then our value started, it started at x equals 2, I believe. Yeah, so it started at x equals 2 right here. Okay. So let's do these. Let me do the increasing, decreasing in green. So I'll put these dots right here, and I'm just going to draw these down. And what I know is that my function increased right here, it decreased right here, and then it increased right here. So I kind of already know a little bit about what my graph is going to do. It's going to go up, it's going to go down, and it's going to go up again. So I kind of know the basic picture. But what these numbers, what these concave up and concave down numbers let me know, is they let me know how my graph is curved. So I know that in this section, it was concave down. In this section, it was concave up. And in this section, it was concave down. So what I know is that even though it goes up and down, I actually know that it's concave down this whole way. So I have this type of shape. So I know it's going to go up, bowl out, and then curve back down like this. So I know it's going to have kind of this shape. I feel like I didn't do a great job there. Let's make it go like that, and then maybe something like that. And then what I know is that it's decreasing here, so now it's going to start flipping the other direction. So I know it's going to bowl like that. And then at this point, it starts increasing again. And so we increase here. And then what happens when we get here? We keep increasing, but we keep increasing at a separate rate. So we can kind of start to see the basic picture of our graph. Our graph goes up, down, and up, but it has curved down in this direction, curved up in this direction, and curved down in that direction. So we have kind of this type of bowl shape. And probably I should have been a little bit more dramatic with this. I think this points over here on the right should be up a little bit and down a little bit, because I think what x plus cosine of x looks like is it kind of looks like a cosine function, except a steadily growing upward cosine function. But you can kind of see it here. But what's nice is once we add cosine, as we add concave up and concave down to our picture, we can start to get where these curves happen in our graph. And that helps us a lot, helps us make this picture a lot. Okay, so hopefully that makes a little bit of sense. I want to talk about one other principle, and the last principle I want to talk about is what we call the second derivative rule, or the second derivative test. The first derivative test was just a way of finding maximums and minimums by looking at where our function increases and decreases. And by the way, if you look on here, you can see here's our maximum, here's our minimum, local max and local minimum. This is an inflection point, and this is an inflection point. So you see when it switched from concave down to concave up, those were our inflection points. It turns out, though, there's another way to think about maxes and minimums, and it happens to come from this question. That is, if it's a minimum, what sort of concavity does it have to have? And if you think about it, you go, well, minimums are always concave up, because if it was concave down, it would have this type of shape, and you can't have a minimum and a concave down shape at the same time. Similarly, maximums have to be concave down. You can't have maximums and concave up shapes at the same time. So the second derivative test simply says this. Test says this: if the first derivative equals 0, and let's add three pieces of information. If our derivative equals 0, then one of three things could happen. Either one, if f is concave up, so if the second derivative is positive, if it's concave up, that means it's positive. That's this type of situation where we have a bowl down. Then we get a local minimum. If that second derivative is negative, then you have to have a local max, because that means we're in this type of situation where you have a concave down shape, right? Finally, you could have that second derivative is equal to 0. And if it's equal to 0, the test fails. You can't use the test. By the way, I won't be asking you to use this test on this semester. This is one that it's kind of a nice test, and there's some places for it. There's some places you'll be asked to talk about it in the homework, but as far as the quizzes or the final exam, this won't be something that shows up there. But I want you to see it. And part of why I want you to see it is because when you go on, especially when you go to Calc 3, we try to find maximums and minimums of multivariable functions. It turns out there's nothing that resembles this first derivative test, but there is something that resembles this. And so this way of thinking, looking at the second derivatives to tell when our functions have maxes and mins, is really valuable when you get to higher variable functions. All right, I hope this makes a little bit of sense. So what I want you to do next is I want you to give two problems a try. So first, try 3.11 and see how you do. So try it on your own. What you're going to need is you're going to need to find where it's increasing and decreasing. So do the increasing decreasing method, then point out the maximum minimums, then do the concave up and concave down method, then point out the inflection points, and then try to put all that together to sketch a graph. So try 3.11. There's a lot going on there, but I have confidence that you can do it. And then the last thing we're going to do is we're going to try go back to that 3.9 problem and try 3.9. It's a little bit more complicated, although it's not super bad. But it's this function that we saw in section 3.1. You have to use a quotient rule to make sense of it. But try those two. I'm going to post those videos separately, and then look at them and see if you got them correctly. All right. Good luck. I know there's a lot going on here, so if you feel a little overwhelmed, if your head is swimming a little bit, this makes you perfectly normal. The key is doing a bunch of these, and another key is coming to see me. So if your head is swimming, you're having trouble, just park in those study hall hours, and we'll just do these problems and do these problems, do these problems until you're comfortable with it. So time is the biggest thing that you can do to help. Good luck, and I'll see you when we try section or exercise 3.11.